Okay, so today we're doing radiation. So we're looking at unstable nuclei, that sort of thing. Our syllabus outcome that we're looking at is to investigate the properties of unstable isotopes using natural and human-made radioisotopes as examples, including but not limited to types of radiation, types of balanced nuclear reactions. So they're the two main things that we're going to look at today. So different types of radiation, and different types of balanced nuclear reactions, as well as what an unstable isotope is. So hopefully you have done the revision at the top of page 58. Let's just go through it. So atoms contain protons, neutrons, and electrons. The atomic number is equal to the number of protons. Atomic mass is equal to the number of protons plus neutrons. And isotopes are the same element with a different number of neutrons. Okay. I should also add that when we've got an element symbol and our two numbers, okay, the atomic number is at the bottom and the atomic mass is at the top. Okay, so just remember those. So let's move on to the first thing. So unstable isotopes. Most isotopes exist in a stable form. So when we say that something's chemically stable, it means it doesn't want to change. It's happy the way it is. Some isotopes, however, are unstable. So meaning their current composition will want to change to something that is a bit more stable. Now, what actually makes it unstable doesn't really matter at this point, but it's basically too much energy. It doesn't like the way it is. Now, these unstable isotopes, they undergo nuclear reactions to become more stable. Now, typically, I'm sure at this point, you're thinking nuclear reactions, bomb blasts, that sort of thing, nuclear reactors. Whenever we say nuclear, it just means of the nucleus. So these reactions aren't going to happen at the electrons like a normal reaction would. They're going to happen at the nucleus. Okay. Now these nuclear reactions, they release one of three different types of radiation. So we have an alpha particle, which is just a helium nucleus. We could have a beta particle, which is just an electron, or we can have a gamma ray, so a packet of high energy light waves. Now, these are the really dangerous ones. These are the ones that cause you radiation sickness. They're really, really not great. Okay. Just as a bit of an aside, the reason they're not so great is um, they are so high energy that if it hits you, it could hit the DNA, somewhere in your skin or even somewhere in your body. And when that happens, it damages that DNA, and so that's how it leads to cancer. And if you get too much radiation, too much damage to your DNA, it just can't replicate, and your cells start dying off. So that's why gamma rays are so dangerous. But I digress. Let's go on and have a look at what those different decays actually do. Okay. So firstly, we have alpha decay. So a nuclear reaction that releases an alpha particle. So remember a helium nucleus. It's called an alpha decay. Losing that alpha particle means the atom which underwent the alpha decay loses two protons and two neutrons. Okay. Now, if you remember, if you lose a proton, you change the atomic number, which changes the type of element that you've got. Okay, so if you undergo a alpha decay, sorry, the atomic number goes down by 2 and the atomic mass goes down by 4. Okay. Here's an example. We got 23592 uranium. When that undergoes an alpha decay, we lose that helium nucleus and we get this daughter nucleus of thorium, which has 4 less mass, 2 less atomic number. Okay, so it's actually changed what element it is. Some examples. So let's go plutonium to uranium with the alpha particle. So we can see that the 239 of the plutonium drops 4 to 235. The 94 drops 2 to 92. And we have that 4-2 helium nucleus coming off. Now it's important with these balanced the balanced radiation or nuclear reactions that we follow through on the conservation of mass, which is that mass doesn't change, it only gets transformed. And so what we want is we want the same number of protons and neutrons on both sides of the reaction. So you just double check, you go 94 is equal to 92 plus 2, so that's good. 239 is equal to 235 plus 4, so that's fine, okay? Having a look at the other ones, so this second one, we have that 235 uranium, that can then go to 231 thorium, just like in the picture previously. We can also write the helium nucleus as just an alpha, okay? So if we write an alpha in the nuclear reaction equation, it just means that helium nucleus. But again, it's gone from 235 to 231, so it's dropped 4, 92 to 90, so it's dropped 2. Another example is radium. So 226 radium drops by 4 to 222 radon plus a helium nucleus. So it's just the same thing over and over again. Now, so have a go at these. So predict the products of the following alpha decays. I've written one of the products there for you, just so you remember that it is an alpha decay. So have a go. Pause the video, and I'll come back in a sec. Okay, so the first one's 214 uranium. Second one should be 218 palladium. And the last one should be 207 TL. What's TL? Thallium, of course. So those ones, make sure you got that right. If you're not sure, go back, have a look at how it works. And if you're still not sure, come see me. Next, beta decay. So a beta decay, a nuclear reaction that releases a beta particle, is called a beta decay. It occurs when a neutron actually splits into a proton and electron. Okay, so we know a neutron has no charge. So what can actually happen is a neutron can split into something with a positive charge and a negative charge. And so that positive charge is a proton, the negative charge is an electron. The electron then gets ejected because it's very high energy. The atomic number effectively goes up by 1, but the mass remains unchanged. So here's an example here. So 137 cesium, it undergoes a beta decay, ejects that electron, a neutron becomes a proton, and we end up with 137 barium. Okay, so if you have a look on the periodic table, it's in the 6th period, group 1 and 2, so it goes from an atomic number of 55 up to 56. Okay. Now, writing them as a reaction equation, because the atomic number goes up by 1, we write this -1 here on the electron. So electrons don't technically have -1 atomic number, but it's just for simplicity in these reaction equations. So we can see that the mass number hasn't changed, so it's gone from 234 thorium to 234 protactinium. The atomic number is increased by 1, so it's gone from 90 to 91. And then we've written this electron at the end here as a -1. Sometimes it might also be written with the charge on it. Okay. Going on to the second one, so we have 214 lead undergoes a beta decay to form 214 bismuth. Again, the atomic number goes up by 1, and this time we've written it as a beta. Okay, so you can write it as the E minus, or the beta. They're all accepted. But the important thing is that the mass doesn't change. Now, lastly, we have 228 radium undergoes a beta decay to 228 actinium plus our electron. So, following that, have a go at that, doing it yourself. Remember, the mass won't change, the atomic number will go up by 1, and you'll have to check your periodic table to find out what that one goes to. Okay, so pause the video, have a go at it, and we'll come back in a sec. Okay, so let's have a go at these. So the first one should be 228.89 thorium. Second one's 234.92 uranium. And then 211.83 bismuth. Okay, so make sure you got those. Again, if you're not quite sure, come and see me and we'll work through it. Now, lastly, we have the gamma decay. So gamma decay, it's a nuclear reaction that releases a gamma ray. The gamma decay occurs when the nucleus needs to shed some energy to become more stable. So much in the way of electrons being able to be excited up into an excited state. Okay, and when they drop down, they release a photon. Nuclei are similar. Now, it doesn't effectively happen in the same way, but it's still excited and it still sheds energy by dropping to a lower energy state. Okay. Um, and again, the energy is released as a light wave, but whereas our electrons falling back to a lower state, so falling back to the ground state, release generally light waves that we can see, so visible light. This light energy is much higher energy. Okay, it's very high. It's gamma rays. Okay, so it's more energetic than UV, more energetic than X-rays. It's up there. Now the thing with the gamma decay, the nucleus doesn't change at all. Okay, it just loses some energy, makes it a bit more stable. So having a look at the examples, nickel goes to nickel plus a gamma ray. Technetium goes to technetium plus a gamma ray. And protactinium goes to protactinium plus a gamma ray. So we always write as 0, 0 gamma, or we can just write gamma by itself. Some people write it as HV, which is a physics thing for photons. You're probably not going to come across that much, so unless you're deep into physics, don't worry about that too much. But we do have that gamma that we're going to use. Okay, so we're not going to do any examples on that because they're way too easy. The last thing we're going to do is this isn't covered in the syllabus so much, but we're going to have a bit of a look at it anyway, is another nuclear reaction called fission. Now, fission, it's a reaction where an unstable nucleus will split into multiple stable nuclei. Now, that can happen spontaneously, or it can happen, when something else hits it. Um, Now, sometimes radiation is also released during these reactions, so you can also have an alpha particle, a beta particle, a gamma particle, or other things. You can get neutrinos, neutrons, antineutrinos, positrons, all sorts of other weird things can happen. But we're just going to have a look at the important point. It's that these equations balance, so that atomic masses and atomic numbers add up to the same on both sides of the reaction. So it's that law of conservation of mass, which we will go into in a lot more detail in Module 2. But just remember, mass doesn't change. Sorry, mass is neither created nor destroyed, it just changes form. And so it should always be the same before and after a reaction. So this is an example of a fission reaction. So this one's 235 uranium plus a neutron. So this one's kind of one that's catalyzed by a neutron hitting the uranium. It doesn't occur as often spontaneously. It forms two different elements. So it splits into barium and krypton. Now, if we have a look at the masses, so 235 plus 1 adds up to 236. 92 plus 0 is just 92. If we have a look at the atomic numbers of our two elements that are formed, 56 and 36, add them together, we get 92. 141 plus 89, what does that give us? 50. Hold on, where's my calculator? It gives us 230. Okay. So realistically, what should happen? I can see I've written the wrong isotope. So that should say 91 krypton. Okay, so that should add up to 232, which gives us those 3 neutrons as extra. Okay. Um, no, sorry, 92. Okay, I'll fix all this up before you I actually give you the booklet. Okay, so 232, and we have the 3 neutrons that make up the rest of the mass. Okay. But again, the fission thing, it's not technically in the syllabus, but you might need to know it. And you will need to know it if you do physics. So that's module 8 from physics stuff there. Now, a little summary of today's stuff. Sorry, back to fission. There's a pictorial example. So our 235U, it gains that neutron, makes it quite unstable. It then splits into our krypton and barium and our 3 neutrons. Yeah, a summary. So unstable nuclei become stable by undergoing nuclear reactions, releasing radiation. An alpha decay involves losing a helium nucleus. A beta decay involves a neutron splitting into a proton and electron. And a gamma decay reduces the energy of a nucleus by ejecting a gamma ray. And the other really important thing, our masses and our atomic numbers should be the same on both sides of the reaction. So our law of conservation of mass. Okay, so just remember that. So get those down and start having a go at the questions on page 62. And that is all for today. Thank you.